Hi, in this presentation, we're going to discuss Newton's third law, and we're also going to talk about momentum. So, in our previous presentations, we've talked about forces as kind of standalone items. We haven't really talked about how they interact, but it's important to realize that in physics, no force ever acts alone. So, for instance, if you're standing there leaning against a wall, you're exerting a force on the wall, but the wall is also exerting a force on you, holding you up. And we call this a force pair. And Newton wrote about this in his third law. And Newton said that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. So, for instance, in our illustration here with the hammer hitting the stake, as the hammer exerts a force on the stake actually pushes back up on the hammer as well. So, thinking about that, say if we're playing soccer and we kick a soccer ball with 150 newtons of force, how much force does that ball exert against our foot? And the ball exerts 150 newtons of force against our foot. And these are called action and reaction forces. So, us kicking the ball would be the action force. The ball exerting a force back on our foot would be the reaction force. And these are co-pairs of a single interaction. And it's important to realize that neither force exists without the other. And just think about, so you kick the soccer ball, the ball exerts a force against your foot. But what just happens if you just kick your foot and don't hit anything? Well, you really haven't exerted a force on anything. Okay? These forces are always equal in strength and opposite in direction, and they always act on different objects. So when we kick a soccer ball, our foot exerts a force on the ball, but then the ball exerts a force on our foot. You may have heard Newton's third law expressed in a different way. To every action, there is always an equal and opposite reaction. So, for instance, when a car is driving on the road, the tires push on the road, and then the road pushes back on the tire. Or even think of a rocket. As we ignite the fuel, the gases that it uses for fuel, those gases push on the rocket pushes on the gases, and the rocket goes up. So let's think about that. You're walking down the street, and when you step off a curb, you can feel the Earth's gravity pulling you downward. What do you think would be the reaction to this force of gravity pulling you downward? And the reaction to that force is actually you pulling the Earth upwards. So when you step off the curb, gravity pulls you down, and your body actually pulls the Earth up. Now, because of the extreme difference in mass between us and the Earth, we get moved a little bit more, and the Earth just moves a teeny tiny infinitesimal amount that we basically don't have the tools to measure. We can see this when we fire a cannonball. So the force that's pushing the cannonball forward is equal to the force that's going to cause a recoil and push the cannon backwards. So the force is the same, but do you think these two different objects accelerate at the same rate? Do you think the cannonball is moving as fast as the cannon moves backwards? Well, let's see. Now, remember, in last week we or in our last presentation, we talked about Newton's second law, which is force equals mass times acceleration. And if we have the same amount of force exerting it, and we exert that on a small mass, we're going to have a very large acceleration. And then the same force exerted on a large mass is going to produce a very small acceleration. So we could probably write our equations like force equals m great big A for the cannonball. And then for the cannon, because it has more mass, we could write the equation force equals a great big M and a little tiny a. And we can actually work this out mathematically too. So let's say the force that's we're exerting to fire a cannonball is 1,000 newtons, and the mass of the cannon is 800 kilos, and the mass of the cannonball is 20 kilos. If we plug this into our force equals mass times acceleration equation, we can see for the cannon, the force of 1,000 newtons equals 800 kilos times A. And if we work that out, we found that A is a pretty small number. It's 1.25. But for the cannonball, it's a little different. When we plug in the mass of our cannonball into the equation, now we have 1,000 equals 20 times A. And when we work out that equation, we get a much greater acceleration. We get 500. So we can see that with the same force on the small mass of the cannonball, it's going to cause a huge acceleration compared to the acceleration it's going to create in that massive cannon. So let's look at this a slightly different way. Say we have a bus driving down the highway and a poor bug is flying and he goes splat and he has a collision head on with the bus. And if you've seen this happen driving down the road, you know usually what happens is your bug gets splattered everywhere. So, thinking about this collision, which would you say is greater, the force acting on the bug or the force acting on the bus? And if you said both are the same amount, you're correct because think about it. We have a very massive object, the bus. We have a very tiny object with very little mass, the bug. And they actually collide with the same amount of force. And just like our cannonball, uh, the bug is going to undergo a very huge deceleration compared to the bus. And if we had sensitive enough instruments and we were uh, evaluating the speed of the bus, when it hits that bug, we would actually be able to see it decelerate just a teeny tiny amount. But it's going to be in proportion to the difference between the mass of that teeny tiny bug and that huge bus. But the force acting on both of them is the same. And also last week we talked about looking at vectors. And we can also use this to talk about Newton's third law. So let's start off by talking about this picture. So we have a girl pulling her pet dog on a sled, and we can see the force, the diagonal arrow F there is the force she's exerting on the sled to pull it. And if we break that down, we can see that the there's a vertical vector Fy of her force and also a horizontal vector Fx. And we can just see by looking that the Fx is, of course, the greater vector. But there's also two other forces that we're not looking at that are acting on this sled. Okay? There is the weight or the mass affected by gravity of the dog and the sled. And there's also the support or normal force pushing back up on the sled and the dog holding it up. Just like when we talked about, we have the force of mg if we put a coffee cup on a table and then the table pushes back up with the normal force against the cup. And this can come into play when we start talking about inclines. So let's look at our little skateboarder here on her skateboard. So if she's on a horizontal surface, the force of her weight acting with gravity pulling her down is going to be the same as the normal force pushing her up. So she's in equilibrium. They're equal and opposite. But once she gets on the incline, okay, now the force of gravity acting on her mass, her weight is the same. But now there's not as much of that weight pushing against the surface she's on. So the normal force is going to be less. And the steeper this incline, the less the normal force is going to get. And we can actually use our parallelograms to draw on here to find that resultant. And then this resultant is what is actually pulling the skateboarder down the hill when she's on an incline. And let's look at this happening with this block of ice. Okay. In the left picture, the block of ice is on a horizontal support force, so its normal force and its weight, the mg, are equal. Okay, as we start to raise the ramp, which force stays constant? And the force that stays constant is our mg. And as the ramp is raised, n starts getting less. N is only going to be the proportion of ng that's still pressing against the surface. So the proportion of mg that's still pressing against the surface is only this long, so n is only this long. And then once we raise the ramp all the way to vertical, okay, now there is no support force because all of mg is going down here. So the net force is the force of gravity on this object. So now that we've talked about Newton's third law, let's move on to momentum. So momentum is a property of moving things. And basically, when we're talking about momentum, we're describing inertia in motion. And remember, inertia just doesn't make things stay still. Inertia keeps things moving when they're already in motion. And we can write momentum by saying it's the mass of an object multiplied by its velocity. And we can write this in an equation. And usually we've already used m for mass, so we're going to use p for momentum. So in equation form, momentum is p equals m times v. Momentum is mass times velocity. So looking at this formula, we can kind of see that if we add more mass, momentum is going to increase, or if we increase the velocity, we're going to increase the momentum. And this kind of makes sense if you just think about things. Um, if we have a boulder rolling down a hill, that large boulder is going to have more momentum than a small pebble that's rolling at the same speed because it has more mass. If we multiplied out the mass times velocity, we'd get more momentum because it has more mass. Conversely, if we have two boulders of the same mass, the one that's rolling faster, the one with more velocity, is going to have greater momentum. And knowing that momentum is mass times velocity, what would you say is the momentum of a boulder at rest? Well, okay, if our boulder's not moving, if it's at rest, then its velocity is zero. And if we multiply the mass, whatever the mass is, times zero, we get a momentum of zero. So if momentum is only a property of things in motion, if they're at rest, you can't have any momentum. Let's look at our two vehicles here. We have a big truck and we have a little beep beep car. If they're both traveling at 60 kilometers per hour, so they have the same velocity, which one would you say has more momentum? Well, of course, the truck is going to have more momentum because it has more mass. And again, momentum is just mass times velocity. So if we increase either one of those, we're going to have more momentum. Let's look here. So we have a bowling ball, which weighs about 5 kilograms, and it's really rolling pretty slowly down the alleyway at about 3 kilometers per hour. And then over here on the right, we have a bullet that weighs about 5 grams, and it's moving at about 3,000 kilometers per hour. So which one would you say has more mass? Well, obviously the bowling ball at 5 kilograms, has much more mass than a 5 gram bullet. Has about 1,000 times more mass. But which would has more momentum? And the answer here is they have identical momentum because even though the bowling ball has more mass, the bullet has a much greater velocity. Okay? And we can multiply this out. So we know that momentum equals our mass times our velocity. So 5 kilograms is 5,000 grams. And if we multiply that times 3 kilometers per hour, we get a momentum of 15,000. And if we go over here to our bullet, it weighs 5 grams, but it's moving at 3,000 kilometers per hour. But if we multiply that mass times that velocity, we get 15,000. So we can see that their momentum is identical, even though their mass is very different and their velocity is very different. So if we have an object and the mass of that object stays the same, but we notice the momentum changing, well, we know then that the velocity must have changed. It must have been accelerated. So acceleration has occurred. And remember, acceleration can be either positive, it's moving faster, or acceleration can be negative, it can be decelerating, starting to move slower. And what do we have that can cause acceleration? And of course, you have to have a force to cause acceleration. And the greater the force that we apply to an object, the greater the acceleration and the greater the change in momentum. But the time that we apply that force is also important. When we talk about momentum, we can also talk about the impulse. And we talked about the force on the previous slide. And impulse is the product of the force we're applying on the object and the time that we apply that force. So in equation form, we can write impulse equals F times t. And if we apply a force, the same force, over a very short period of time, we're going to get a smaller change in momentum than if we apply that same force over a longer time. So if we apply the same force for twice the time, we're going to impart twice the impulse. And the greater the impulse we exert on something, the greater the change in momentum. The impulse equals the change in momentum. So we can write this in equation form as Ft, which is impulse, equals the change in, which is that little delta sign there, that triangle, momentum, which is mass times velocity. So if your car is stopped and you exert a force to push it to try to start it, if you push it for 1 second, you create a certain change in momentum. But if you exert the same force for 2 seconds, now you're going to double that change in momentum. And let's see how this can work sometimes. So think about if you go golfing or you play baseball. When you go to hit the ball, you're probably told to try to apply the greatest force for as long as possible to extend that time of contact, to follow through. And if you can, say, hit a golf ball with a certain amount of force, if you can follow through and have that club imparting that force to the golf ball for the longest period of time, you're going to get a greater change in momentum. You're going to increase momentum. Okay. Same thing when you hit a baseball. If you can keep the bat on the ball for a longer period of time, you're applying that force for a longer time. You have a greater impulse and you're going to have a greater change in momentum. So in our previous example, we kept the force the same, but we just increased the time to um, make a greater impulse and increase our momentum. But we can also do it to decrease momentum. So let's say you're driving down the road and all of a sudden you find out your brakes don't work. And up ahead of you, to stop you, you can either hit a brick wall or a nice big fat haystack. And which would you choose to hit? And usually, even if you haven't studied momentum or impulse, you're going to say, well, of course, I'm going to hit the haystack, right? And if we think about the equation for impulse momentum, it's Ft, or force times time, equals the change in momentum. So if we look at this diagram, we can see. So we have the same momentum, okay, in both pictures. When we hit the haystack, have increased the time, so the force of our impulse is going to be really small. Okay. So as we hit the haystack, it takes us a long time. That force is absorbed by the haystack over a long period of time. So it's going to be a small force over a long period of time. But when we smack that brick wall, all of our force is imparted in a very short period of time, like a millisecond. So the force is very great. So if we're driving fast and we hit a haystack or we hit brick wall, we're going to get very different results. So would you say that both these cars, one hitting a haystack and one hitting a cement wall, experience the same change in momentum? And do they both experience the same impulse? And do they both experience the same force? And if we go back and look at the picture, yes, they're going to both experience the same change in momentum because the velocity is going to change to zero. So the momentum is going to change the exact same amount in both of these pictures. And the impulse is also going to be the same because if we multiply, say, our small force times big time, we're going to get the same result as if we multiply a big force times a small time. So let's say here, um, our the change in momentum, let's just say it's 10, okay? And so over on our haystack, we can say our force is 2 and our time is 5, okay? But down here, if our change is 10, we can say our force is 5 and our time is 2. So it equals the same. The impulse is the same and the change in momentum is the same. But the force is going to be vastly different. So our answer to the questions 1 and 2 is yes, and our answer to question 3 is absolutely not. So using the same principle, if you've ever watched boxing or martial arts, when a punch is coming in, fighters are taught to lean away from the punch. And this way, this if we lean away from the punch, this increases the time that it takes that punch to land and decreases the force, even though the change in momentum is the same. If the boxer leans the wrong way and he leans into the punch, well, now we've decreased the time and the force is going to increase, and that's going to increase his chance of getting knocked out as well. We can also have conservation of momentum. And the law of conservation of momentum says that in the absence of any external force, the momentum of a system remains unchanged. So when we fire a cannon, the force on the cannonball inside the cannon is equal and opposite to the force of the cannonball on the cannon itself. The cannonball gains a certain momentum, while the cannon gains an equal amount of momentum in the opposite direction. The cannon recoils. When no external force is present on this system, no external impulse is present, and momentum cannot change. And so we can see this in the conservation momentum on our diagram of our cannon and cannonball here. So when we fire the cannonball has a momentum of a very small mass and a large velocity, and the cannon has a momentum of a very large mass and a small velocity. And we can use the conservation of momentum when we deal with collisions as well. And this says for all collisions in the absence of an external force, the net momentum before the collision equals the net momentum after the collision. And we can write it as an equation as the net mv before is going to equal the net mv after. And of course, mv standing for mass times velocity. There's a couple of different kinds of collisions. There's elastic and inelastic. And elastic occurs when colliding objects rebound without any lasting deformation or generation of heat or without sticking to each other. So, for instance, in A, we can see here our yellow ball is nice and still. The green ball comes and collides with it, and now that momentum is transferred to the yellow ball and it's moving. In B, we can see where the yellow ball and the green ball hit head on and bounce off each other and go in opposite directions. And then in C, we can see the yellow ball is kind of puttering along at a slow velocity. The green ball is moving at a much faster velocity, does kind of a rear end collision, and the end result is now the yellow ball has the greater velocity. Inelastic collisions occur when these objects collide and there's some type of deformation or generation of heat, or the objects are stuck together. So that would be an inelastic collision. One example of an inelastic collision might be if we have two freight cars colliding. So let's say we have a single freight car and the red freight car, and he's moving at 10 meters per second. Now on the track is another freight car, the exact same mass, our green freight car, and it's at rest. And so if these two collide, what is going to be the ending velocity? So we know because of the conservation of momentum that the net momentum or mv before has got to equal the net mv after. So let's put in the information we have. So before we have one mass, the red freight car moving at a velocity of 10. So 1 times 10 is 10. After the collision, now we have two masses times v. So 2 times v has to equal 10. And we divide 10 by 2, and we get the ending velocity of the two cars stuck together is going to be 5 meters per second. Now, what happens if the objects are moving in opposite directions, like a head on collision? Well, if they have equal momentum, then we're going to consider one object's momentum negative, just like last week when we talked about um, opposing forces on an object. So we can say the gray car has a positive momentum. We'll consider the white car's momentum negative. At the point of collision, we can add those two momentums together and they'll equal zero. And the colliding objects and the cars in this case come to rest at the point of impact. Sometimes our colliding objects are not moving in the same straight line, either one hitting the other from behind or in our head on collisions. In this case, we can create, as we did last week, a parallelogram of the vectors to find the combined momentum. So in this particular diagram, momentum of car A, the little red car is moving eastbound, will be our horizontal vector, and our vertical vector will be car B, the little purple car moving northbound. And so we could draw these vectors and we could use our parallelogram theory to get the resultant, which would be the combined momentum of A plus B moving off to the northeast. So to summarize Newton's three laws of motion, the first law of motion, the law of inertia, says an object at rest tends to remain at rest, and an object in motion tends to remain in motion at constant speed along a straight line path. Our second law of motion, the law of acceleration, says when a net force acts on an object, the object will accelerate. This acceleration is directly proportional to the net force and inversely proportional to the mass. And we can write this law as an equation, F equals ma. Newton's third law of motion, the law of action reaction, states whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first.